Let's take a look at an example problem for ME111 in Module 7.1. So in this example problem here, we have a hydraulic piston and a load. So the figure below shows us a double acting piston and a cylinder. It tells us that the device moves some load mass M in response to the pressure sources P1 and P2. So here's our load mass M, here's our pressure source P1, and here's our pressure source P2. We're supposed to assume that the fluid is incompressible, the resistances are linear, and the piston mass is included in the M down here. So this whole piston mass here is included in this M here. Now they ask us to derive the equation of motion for M. So now that we've had that opportunity to read through the problem statement, understand what they've given us and what they're asking us to solve for, the next thing we want to do is create our setup page here. So this is for ME111, my example problem 7.4.7. It's a hydraulic piston and load, a double acting piston and cylinder. And what's given to me? Well, I know my mass is M, P1 is pressure source 1, P2 is pressure source 2, my PA is my atmospheric pressure, R1 is my resistance 1, and R2 is my resistance 2, and I'm looking for my equation of motion for M. So I redraw out my diagram down here. Here's my atmospheric pressure on both ends here. Here's my pressure source 1, my pressure source 2, my resistance 1, resistance 2, internal pressure P3 and P4 here, and my mass M that combines this as well as the piston. So assumptions I'm supposed to make: fluid's incompressible, resistances are linear, and the piston mass is going to be included in this M down here. So from that there, we can now start our solution. We can reference back to our setup page and our problem statement page for any questions we may have for given information and what they're asking us to solve for. So the first thing we want to do is we want to define pressures P3 and P4 to be the pressures on the left and right hand sides of the piston. So we can reference back to that diagram there and understand where those are. For our general equation for start the solution here, what I'm going to do is reference equation 7.35 from our text, that our Q sub n is equal to P over R sub R, where Q sub m is our mass flow rate, P is our pressure, and R sub R is our linearized resistance. So from that there, we can take this relationship and then create equations 1 and 2 by looking at our initial given diagram on the next slide. I'll reference back to that in order to see where our pressures lie relative to our resistances to figure out our mass flow rate equations. So that's what I do here. I reference back to my initial given diagram here, and I say, okay, let's start with the left-hand side over here. Well, I'm looking for my mass flow rate for this, for the first side over here. So when we're dealing with resistance 1 right there. So to come up with this relationship for our mass flow rate, what I want to do is take a look at my pressures and my resistances. So I can see I have my PA, my P1, and then I go through this resistance 1 right here, and then there's my P3. So I'm going to have a P1 plus my PA minus, once I go past this guy here, my P3 times my 1 over R, and this comes from that equation, our general governing equation that we're going to use. So these are my P's right here, P1, PA, and P3, where the P1 and the PA are positive. Now I'm going to do the same thing over here through my R2 here. We can see, okay, I start off with my P4 over here, so there's my positive P4, go through my R2 here, and now I have my P2 and my PA, so it's a minus P2 minus PA. So my general equation here now for Q sub M2 is equal to 1 over R2 times P4 minus P2 minus my PA. So that's how I use that initial given diagram to come up with these two relationships for mass flow rates. So as we continue on with our solution, the next thing we're going to take a look at is our conservation of mass. Now from our conservation of mass, we can get that QM1 is equal to QM2. We can also figure out that QM1 is equal to rho A x dot. So with this, equations 3 and 4 now from our conservation of mass, the next thing we want to do is combine all of our equations 1, 2, 3, and 4 together. So over here I've rewrote out 1, 2, 3, and 4. So what we're going to do for these ones is start combining them. So to combine, what we can do is we can plug our rho A x dot from our equation 4 here into QM1 and QM2. So that's what I do is I plug in for both of those, and I can plug in that our QM1 is our rho AX, which is equal to, now from equation 1 up top here, 1 over R1 plus P1 plus PA minus P3. Now what I can do down here is do the same thing for our QM2, equation number 2, plug in for QM2 of this rho AX dot here, plug that in, rho AX dot is equal to the right hand side of our equation 2, 1 over R2 times P4 minus P2 minus PA. So then what I can do is let's take these R1s and R2s, multiply them over to the other side there, so we end up with our equations down here that we have R1 rho AX dot is equal to P1 plus PA minus P3, get our P's all together on one side, and then we'll also have, when we do that for our equation 2, we end up with R2 rho AX dot is equal to P4 minus P2 minus PA. To get these new equations, equation number 5 and equation number 6 right here. So I rewrite out equations 5 and 6 at the top of my page here. So let's add these two together. There's multiple ways that we can do this. What we're trying to do is to rearrange this here and simplify them down. And the first thing I can do is to add them together. And what that will do when we add these two equations together is you'll see that if we add all our p's together, we have P1 minus P2 minus P3 plus P4 plus PA minus PA. So those two will cancel out. So we'll eliminate a PA when we add the two equations together. And this is equal to, we add our other sides of these together, R1 plus R2, plus we have a common rho AX dot there. So we can pull that out. Simplifies down to P1 minus P2 minus P3 plus P4 is equal to R1 plus R2 times our rho AX dot. So what I want to do now is I want to solve this for P3 and P4 and get those together on one side by themselves. So we do that now here, and we see that we have P4 minus P3 is equal to P2 minus P1 plus my R1 plus R2 times that common rho AX dot here. So I'm going to call this my new equation, equation 7. Now this was one way to do this, is by adding the two equations together. We could also solve both 5 and 6 up here, 5 and 6, for our PA, set the PAs equal to each other, and solve that way. So let's try that here, just prove to ourselves so we can do this an alternate way to come up with the same answer here. So I have my equations 5 and 6, so we'll solve them both for PA. So let's just take a look at equation 5 first. If I want to solve equation 5 for PA, what I can do is move our P1 and our P3 over the other side there, so I can subtract a P1 and I can add a P3, so we end up here at PA is equal to R1 times rho AX dot minus P1 plus P3. So now I can do the same thing and solve for PA here from equation 6. So what I'm going to do is move my PA over to the other side, add that there, and subtract my R2 minus rho X to leave me with a PA is equal to negative R2 rho AX dot plus P4 minus P2. So now I can set equations down here, this rearranged version of equation 5 and equation 6, solve for PA, set those now equal to each other because they're both equal to PA. So what I end up with is R1 rho AX dot minus P1 plus P3 is equal to negative R2 rho AX plus P4 minus P2. So I could add a P2 to both sides. I could subtract a P3 from both sides, and I could add this R2 rho AX dot to both sides. So that goes away here. We can put that back over on the other side. P2 goes away here. P3 goes away there. What we end up with, if we try to get our P3 and P4 alone together on one side, we end up with our R1 rho AX dot plus R2 rho AX dot plus P2 minus P1 is equal to P4 minus P3. I can again pull out my rho AX dot there, so R1 plus R2 rho AX dot plus P2 minus P1 is equal to P4 minus P3. Just rearrange it, and I end up with the same exact expression I found on the previous side by adding the two equations together, but now by solving for my PA and setting them equal, I get the same expression. So there's multiple ways that we can solve those two equations in order to rearrange and get them in terms of P4 and P3 and eliminate our PA. So recall what we're looking for is our equation of motion. We're dealing with equation of motions. What we want to do is look at Newton's second law, which is F is equal to ma, but we also remind ourselves if we have F and we're dealing with pressures, the pressure is our force over area. So we can solve that, rearrange and solve for force. So force is equal to pressure times area there. So now we can start rearranging Newton's second law a little bit here and say, okay, well, our A is going to be our x double dot for our case here. So we can replace ma with m x double dot because acceleration is the second time derivative of our position. And for our forces, the forces that are going to be applying for us is our pressure times area there. So now we end up with the expression mx double dot is equal to PA. And for us here, we're dealing with our pressures P3 and P4. If we go back to our initial diagram, we can see those are the two pressures that are going to be involved in our force here. So we end up with our new equation 8 here, mx double dot is equal to area times our pressures here of P3 and P4. So as we continue on with our solution here, what we want to do next is plug equation 7 into equation 8 in order to get our desired model. So we take a look down here, rewrite equation 7 and equation 8. Equation 7 is P4 minus P3 is equal to P2 minus P1 plus my R1 plus R2 times my rho A x dot. My equation 8 from Newton's second law was my mx double dot is equal to A times P3 minus P4. So if we notice the difference between 7 and 8 is 7 is P4 minus P3, whereas in 8 we have a P3 minus P4. So when we plug equation 7 into equation number 8, what we want to do is negate the right-hand side of that equation to get it in the form of P3 minus P4. So I do that there. Now my equation 8 is mx double dot is equal to A times P3 minus P4. So P3 minus P4 now becomes negative P2 plus P1 minus my R1 plus R2 times my rho A x dot. See that there's an A here that I can distribute through, so this becomes mx double dot is equal to negative A P2 plus AP1 minus R1 plus R2 times my rho times my now A squared x dot when I distribute that A through there. So I pull out my negative A there. We have mx double dot is equal to negative A times P2 minus my P1 there minus R1 plus R2 times my rho A squared x dot, or mx double dot is equal to, if I distribute the negative through, A times P1 minus P2 minus my R1 plus R2 times my rho AX here. So I'm going to move this around, rearrange a little bit, put that in the middle, and we end up with mx double dot plus my R1 plus R2 times my rho A squared x dot is equal to A times P1 minus P2. Call this my equation 9 here. And one thing to note here is that if resistances are 0, then the x dot term disappears, and what we're left with is just mx double dot is equal to A times P1 minus our P2 value right there.